Today we'll talk about yield management for an airline. The problem is we want to determine a policy to accept or decline or stop accepting reservations for the business section of an airline. Okay? So typically, airline companies sell more tickets than the capacity. So if the capacity of the business section is 32, then the airlines may sell more than that. They may sell 40 tickets. This sounds like a little bit crooked, but it is not. The reason they do it is because there is a chance that customers will not show up. And in case that they don't show up, they don't lose their ticket, or they don't lose completely their money. So some customers, if something goes wrong in their schedule, they may cancel the reservations at the last moment or even not show up. And there is a probability that the customer may not show up. So you have to prepare for this eventuality. Okay, so what we know in the problem is that the capacity, which is fixed. So the capacity, let's say, is 32 seats. The demand is not deterministic, it's random. Sometimes we have demand for a large demand, sometimes the demand is low and the airplane leaves and not all the seats are filled. Okay? So the demand is represented by a random variable. So the demand, which of course is deterministic, D, which are the attempted reservations, is Poisson. It's represented by a discrete variable that follows the Poisson distribution. The mean value of this Poisson variable is 44 reservations. Okay, so although 32 seats are available, on average 44 people try to reserve seats. Okay, so there is an extra 12 reservations that exceeds the capacity. Okay, now here is the problem. Some people who make reservations don't show up. Okay, so the probability that the customer who made reservations will show up is 80%. The rest of the probability, 20%, is the probability not to show up. Okay, so probability that customer who made the reservations will show up is 80% or 0.8, okay? Now, the profit per occupied seat is $600. This is profit. If a customer shows up and there is no seat available because they have been sold out, then the airline provides some amount of money besides the ticket, provides $300 as a compensation. So the loss to the airline per unfulfilled claim is $300. And if a customer doesn't show up, although made reservations, there's no penalty. That means the customer doesn't lose the money. Either says, okay, I'm not going to fly, so give me my money back, or if wants to fly in the future, then a new reservation can be made without any cost, okay? So, no penalty for not showing up. Okay, so this is nice. Someone can change his mind or her mind in the last moment and just cancel the reservation or and get back the money. This is as you see, something perk for business class. Okay, if you want to pamper the customers who pay quite a bit of money. Okay. On the other hand, the airline can sell more seats that are available. Okay, and it will have to compensate the customer by $300. Okay, so given all these rules, we want to find the optimum quota to maximize profit. So the objective is find a quota. That means where do you stop accepting reservations if you are the airline to maximize profit. And when we say profit, we mean expected profit. Okay, so Q is the quota. You accept up to Q reservations. NQ, let's define some notation, is the number of customers who claim their seats. Okay, just to explain the Poisson distribution, which is the distribution of the number of attempted reservations. The Poisson is a discrete distribution distribution that models the number of events, random events that occur during a fixed period. Okay? So just to explain this distribution and justify why it is appropriate for this problem, note Poisson is a discrete distribution, obviously, because the reservations must be integers. So it is a discrete distribution. That models the number of random events occurring in a fixed period. So if you consider that customers arrive on the counter, or they call, and the arrivals are random, then the total number of arrivals in a period, say 2 days, is governed by the Poisson distribution. Okay? The time, this assumes that the time between successive events is exponentially distributed the time between successive events is exponentially distributed. Okay? If they are exponentially distributed, the time that it takes from one occurrence of an event to the next is random and independent from one event to the other. Okay, so let's make a strategy to solve the problem. Well, certainly we'll start with the obvious fact that the airline should at least accept a number of reservations equal to the capacity of the business section. So if the airline can accommodate for sure 32 passengers, then should accept at least 32 reservations. Okay? So now what we're going to do is consider that the 32 reservations have been made. And then we accept an additional reservation. When we accept the additional reservation, we may make some profit if we're able to cover the demand, or we may lose money. So we consider that we do 33 reservations, we accept one more, and then we see what happens. Does the expected profit increase or decrease? If it increases, then we go to 33, we consider that we can make 33 reservations, okay? Otherwise, we don't move the quota. We keep it at 32 and the problem is solved. So suppose that we got 33. Now, we consider the scenario, but that we increase the quota to 34. Do we make an additional profit? If we do, then we go to 34, okay? And then, once we have 34, we repeat the process. That means we consider what will happen if I make 34, 35. I bump it up by one seat. So again, we check what happens. If the profit keeps increasing, we'll keep increasing the reservations until the profit starts going down. So this is the logic to find the optimum number of reservations. It's like trial and error. You try to increase the quota, you see if you make profit, then if you do, you increase by another unit, and you continue the process until you get to the point that you start losing money. Okay, so here is the flow chart of the process to define or determine the optimum number of reservations. So we select the Q, the value of Q. Okay, if it is 32, we said that we should start from 32 because we have already 32 seats. Then we consider what will happen if NQ is less than 32, that means less than 32 passengers showed up, okay, less than or equal to that. And then in that case, the profit is $600 per passenger times the number of passengers who showed up, okay? If NQ is greater than 32, more customers showed up. Then the profit, if we if we bump up the reservations, will be 600 times 32 minus NQ minus 32 times 300. Okay. Then we consider the case where we have 33 reservations, and we do a similar calculation for 33. We do the same calculation for 34, the same calculation for 35. Okay. So let's talk about the definition of the optimization problem. Optimization problem. The problem is to find the quota. This is the design variable or decision variable, Q, quota, to maximize expected profit. That's the objective function. So we do the process that we described is called marginal analysis. So we perform marginal analysis, which is what happens if I increase the quota by 1 unit? What happens to the profit the expected profit to be precise, if I increase the quota by 1 unit. So catalytic question catalytic question. What happens to the profit if I'm at a particular number of reservations and I increase it by 1? What happens to the profit if I increase quota, I mix the airline, by 1? That's the question. Okay, increasing the profit in the expected profit from going from Q accepted reservations to Q plus 1, okay? It's called expected marginal profit. Okay, let's define some notation. NQ would be the number of customers that show up to claim their seats out of Q customers who reserved them. Okay? So NQ is number of customers who reserved a seat and claimed it. Okay? And this number is actually less than the number of reservations because some customers don't show up and they don't pay any penalty. Okay. NQ, the number of customers who reserved the seat and claimed it, is binomial, follows the binomial distribution. So it is binomially distributed. With number of trials equal to n, I'm sorry, to q. So let's make a decision tree that shows what happens if we increase the number of the quota by 1. Okay, so let's say the quota increases from Q to Q plus 1. Then two things may happen. One is that the demand is less than Q, the original value, of customers who claim their seats actually less than or equal to Q. So in that case, the increase does not affect the reservations. Increase in quota does not affect reservations. So we accept the extra reservation. On the other hand, the demand may exceed Q plus 1. That means more customers show up. Okay, if this is the case, this is bad luck because we'll have to reimburse the customer if the customer shows up. So we consider now the probability that the extra customer will show up or will not. So the customer may not show up, so this will happen with probability 20%. Customer does not show up, or the customer may show up. Customer shows up. Okay. If the customer doesn't show up, nothing happens. The expected profit doesn't change. If the customer shows up, we have to examine what will happen. Do we have enough seats to accommodate the extra customer or not? So we have a random event here. So if NQ is greater than 32, that means the number of people who showed up is greater than 32, then we lose $300 as an airline. So the outcome is $300 lost, okay? So there's no seat in this case. So we compensate the customer paying $300. So we lose $300. Otherwise, if we can accommodate the customer, because several customers did not show up, if NQ is less than 32, we get an extra $600, okay? So this is the tree that shows what will happen if we increase the quota by 1 unit. So we'll calculate the expected increase in the profit because we increased the number of reservations that we can accept, and then if it is positive, we increase the reservations by 1 unit. Otherwise, we don't. And the process is continued until we find that the expected profit starts decreasing. Okay, so let's write some equations about the expected monetary profit from the increase in the reservations by 1. So EMP, the expected monetary profit, if we go from Q reservations to Q plus 1, is equal to the probability that the demand is greater than or equal to Q plus 1 times 0.8, which is the probability that the customer will show up, times the probability that NQ is less than 32. That means we can accommodate, we have a seat to accommodate the customer. And in this case, since we're calculating the expected profit, we multiply by the extra profit. Okay, this is the one bit eventuality. So this is the expected profit if we can accommodate the extra customer. And we have to consider the other case where we cannot. So if if the probability that the demand is greater than Q plus 1 times 0.8 times the probability that NQ, the number of required or requested seats or reserved seats, is greater than or equal to 32. Okay? So we cannot provide an extra seat, so we compensate the customer by paying $300. So this part is the conditional expectation of the extra profit if we accept an extra reservation, and this is the conditional expectation of the profit if we accept the reservation and the customer didn't show up. I'm sorry, we don't have a seat available. Okay? So this is, let's do the algebra. This is P, D, greater than or equal to Q plus 1.8 times P, the probability that NQ is less than 32 times 600 plus probability that D is greater than or equal to 2 plus 1. That means we cannot accommodate the extra customer. Times 1 minus the probability that NQ is less than 32. Okay. Times minus 300. So all we did, compared to the previous equation, we expressed the probability by 1 minus the probability of the complement. Okay, so this is equal to the probability that the demand is greater than or equal to Q plus 1 times 0.8 times the 1, probability that NQ is less than 32, so we can accommodate the customer, times $600 that we make, minus 300 plus probability NQ less than 32 times 300. Okay, and if we combine the terms to get a nice concise expression, the expected monetary profit from increasing the quota by 1. So going from Q to Q plus 1 is equal to the probability that the demand is greater than or equal to Q plus 1 times 0.8 times 900 probability NQ less than or equal to 32 minus 300. Okay, let's make the 900 a little nicer. Okay. And this is the final expression which gives you the marginal profit. You can program this equation and then start increasing the quota until the marginal profit becomes negative. Okay? So, marginal profit is positive if and only if, so the symbol is if and only if 900 times probability of NQ less than 32 minus 300 is positive. Okay, so we check this expression, which is 900 times probability that the number of customers who claim seats is less than 32 minus 300. Okay. Or equivalently, if 900 times P NQ, the number of attempted reservations is less than or equal to 31, is greater than 300. Okay, so this is the condition that we want to check. Just comparing this number with the right-hand side. Okay, now as we increase the number of reservations that we accept, then the probability of no more than 32 customers claiming their seats, probability that no more than 32 customers will claim seats goes down. Okay? You have less and less chance as you keep increasing the quota to be able to fill, to accommodate the customers. Okay? That means at some point the expected monetary profit when you go from Q to Q plus 1 decreases with Q. That means every time you bump up the quota, the gain that you make, the expected gain in the profit, keeps decreasing because you are taking a higher risk not being able to accommodate the customer. Okay? So, the optimum Q, which will be denoted by Q star, is the smallest number for which the expected monetary profit, the additional monetary profit, is positive. So this is the conclusion. The optimum quota, that means the number of customers that you will allow to make reservations, is the smallest number for which this quantity is still positive. Okay. So let's show a flow chart together with the commands that we use. If we use Microsoft Excel, let's make a flow chart to determine how to determine the optimum number of reservations that should be accepted. So, flow chart, here is the algorithm. For quota optimization. Okay, we start with Q equal to 1, 31. We could start with 1, but we'd find the obvious that until 31, get to 31, then we should accept the reservation. So we start with Q equal to 31, then we add one more reservation that we want to accept, so Q becomes Q plus 1, and then we check the condition, whether we'll increase the profit if we do so. So we have an if statement here, or a conditional statement, is 900 times the probability that NQ is less than 32 minus 300 positive. Okay, that's the catalytic question that we ask. And if the answer is yes, then we do increase the reservations by the allowed reservations by 1. So if the answer is yes, we go to this block and increase the reservations. If the answer is no, then the optimum is we don't increase the number of reservations, so Q optimum is actually the Q that we try less than 1. Okay, so this is the flow chart. And some commands that we want to use if we are writing an Excel program to implement this algorithm are first the command for Poisson distribution, and the other is for the binomial. Poisson is the number of events that occur in a certain fixed period. So the probability that the demand will be greater than or equal to Q plus 1 is equal to 1 minus the probability of demand being less than or equal to Q. And the statement in Excel is 1 minus Poisson and then the statement in Excel takes 3 arguments. One is the value of the demand D, then the probability to show up, the extra customer that will show up, and that probability in our example is 0.8, okay? And the last argument is true. True means that we have a cumulative distribution. We are asking Excel to determine the cumulative distribution rather than the probability density function, okay? So true means that we are requesting cumulative distribution. CDF, cumulative distribution function. The probability that NQ is less than 31, this, the number of people who take reclaim their seats is binomial, so we use the binomial distribution, which is, this is the notation in Excel. So it is 31, the quota, so Q is the quota, the probability, which is 0.8, and true, again true, defines the cumulative. So if you use this statement in Excel and you calculate the value for a particular quota, say 33 or 34, then we'll find what is the probability that will be able to accommodate that number of reservations. So if Q was 33, this will give you the probability that the will be able to accommodate 33. If there are 33 reservations, the probability to accommodate them. Okay. If you want to, I will write an equation that you can use if you want to calculate expected profit. not just for an extra reservation, but for as a function of the number of reservations that are accepted, expected profit for accepting NQ well, the profit will write the expression for the profit and then the expression for the expectation of the profit. So the profit will be I NQ less than or equal to 32. This is an indicator function which is 1 if the condition in the parenthesis is satisfied, otherwise it's 0. Okay? So this is 1 if condition is satisfied. And it is 0 otherwise. Okay, times $600 that we made times N2 plus I NQ greater than 32 times, now we start making losses because we cannot accommodate the customer. So 600 times 32, the profit that we make from the 32 customers that showed up, minus the loss because we extra reservations and we had to compensate the customers for $300 each. Okay? So this is the expression for the profit. Okay? So this is continuation of the equation. Now, to find the expected profit, you need to find the probabilities of the two events. So the expected profit is the conditional expectation of the profit given that NQ is less than or equal to 32 times the probability of NQ being less than or equal to 32 plus E profit given that the number of reservations is greater than 32 times P NQ greater than 32. Okay. And final expression for the expected profit is the probability that NQ is less than or equal to 32 times 600 times NQ plus probability that NQ is greater than 32 times 600 times 32 minus the conditional expectation of NQ, given that NQ is greater than 32 minus Q times 300. Okay. And this completes the solution of the problem for determining the number of reservations that, or the quota that an airline should permit, assuming that the objective is to maximize the expectation of the profit.